So this is a straight to the web special, and this is a replacement for a lost lecture 2 in lecture series on Morse theory and surf theory, and the original happened on January 11th of 2012. And let's see if I can replicate what I said some number of months ago. So, in the preceding lecture, I had given an assignment, which was, which I'll summarize quickly. And you were supposed to imagine S2 embedded inside R3. We call this sigma. There's a particular embedding of S2 inside R3. And then, let's suppose the origin is here. And then you were to imagine then that for any given direction, V, any given direction vector, you could project the surface sigma, you could let f sub v equal projection from sigma onto the one-dimensional subspace spanned by V. And then you think of that one dimension, and then using V itself, you then identify that one-dimensional subspace with R. And so you get f sub v for each V is actually a map from the surface sigma to R. So you get a parameterized family, and its parameterized V itself can be thought of as a point in the unit 2 sphere. There's a unit 2 sphere, and for every direction in the unit 2 sphere you get a projection. So of course, f sub minus V equals minus f sub V, for example. The one thing I wanted to add to that assignment was that the way I've drawn it, it is obviously rotationally symmetric around the z-axis. So really, in some sense, really the only issue is the circle's worth of directions. So the first point is that, really what matters is, well, the point is that whatever you get, what the observation to make is that whatever you get will be rotationally symmetric with respect to rotationally symmetric in S2. Oh, sorry, I didn't. So the question was to somehow graph the critical values of this function as a function of S2, of where you are in S2. So you would have a map, you would have some graph which sits inside S2 cross R, which is the image of the critical values. I mean, the critical values being images of critical points. And for every point in V, you would have, every point in S2, you'd have some number of critical values. And again, the point is that when V is straight up and down, you're going to have 2 critical values. When V is points in the equatorial direction, you'll have 1, 2, 3, 4, 5, 6 critical values, and they change somehow. So the first correction or observation to make was just that this is rotationally symmetric, and so really saying it's over S2 is kind of a distraction. It's really a circle's worth of things that matter. However, then I wanted to say change it. So new assignment, next version is do this for the following surface. And so now I put some genus in there, and now I again put the origin there. And so if this is my new sigma, then again I get f sub v from sigma to R, and then I want to plot. Now the point is this is not rotationally symmetric, and you want to plot critical values as a function of v in S2, and now you don't expect things to be symmetric, so now you have something interesting in that. So your graph of critical values will live in S2 cross R, which may be hard to draw, but that's the assignment. Okay, so having clarified that, I will now resume the actual flow of the main flow of the lecture. The point of bringing up that was simply to break the rotational symmetry and make it more interesting. Okay, so in the entire first lecture, I didn't really give a proper definition of a Morse function. This is a course on Morse theory, so let's start with some, in particular, I didn't really talk about what happens to your boundaries. And so the two cases that we really want to think about are where I'm going to have a map F from some manifold of some dimension n to some one-dimensional manifold. And a one-dimensional manifold, what does that mean? Well, it's either R or an interval. Everything's compact, so say 0, 1, or maybe a circle. You could imagine, mapping to disjoint unions of those things, except then you'd be thinking, your domain would want to be disconnected as well, and then you might as well just look at what's happening on each path connected component. So we can just assume everything's connected. And then the cases we really want to bear in mind for X are X can either be closed or a cobordism is what we want to have in mind. The cobordism means that, and I'll state a definition that doesn't depend, it works, it's slightly more generality than this, but what you want to think of for a cobordism, closed means compact and boundary. Okay? Cobordisms are compact manifolds with not necessarily empty boundary. And a cobordism just means that X is compact and the boundary of X is naturally splits into a disjoint union of two parts, which we call M. Let me see what I'm calling them. Don't want to call them 0. Yeah, M0 and M1. M0 disjoint union M1. These are going to be manifolds of dimension n-1. And the picture you should have in mind, the typical picture for cobordism might be something like this. Genus, this is a two-dimensional cobordism. This is X, it's two-dimensional. Here is M0, which is a one-dimensional manifold, which happens to be a disjoint union of two copies of the circle, to M1, which is a single circle. That's a particular example of a cobordism. And of course, I didn't say that these things had to be non-empty, so these things could be empty. So a closed manifold is a special case of a cobordism. And again, the examples you want, really what you want to think is that if X is closed, then F is going to map from X to either R or S1, and if X is a cobordism, what you want to think is that F is going to map from X to the unit interval, or some compact interval. Sometimes it's useful to have other compact intervals, and then the special thing you want to think, the picture here is that this cobordism we're going to map to the interval from 0 to 1. Think of it as like a height function, and so the M0, which is the bottom end of the boundary, is going to map to 0, and the top end is going to map to 1. But let's say that in a more general way. So let's actually write a definition then. A smooth function, remember everything here is smooth, manifolds, functions, everything is smooth, so smooth function f from xn to y1 is Morse, or is a Morse function, if certain things are satisfied. So the first thing is, I'll do it in. The first thing has nothing to do with what happens on the boundary. The first thing is what I talked about in the previous lecture, which is saying that for each critical point, so remember, critical points are in the domain. For each critical point P and X, I can find coordinates around P and F of P with respect to which So in those coordinates, I'll have some coordinates x1 up to xn here, and some coordinate y, little y, let's say, in the neighborhood there, with respect to which f of x1 up to xn is equal to minus x1 squared minus dot 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 minus xk squared plus xk plus 1 squared plus dot 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 plus xn squared. So some squares with k of them having minus signs and the remaining having plus signs in front of them. So we're supposed to think that this is like the generalized saddle. Of course, k could be 0, k could be n, in which case, if k is 0, there's no minus sign, if k is n, there's no plus signs there. So that's what should happen near a critical point. And then the second thing is that x should be compact. So this is really funny to say that that's a condition on the function, but anyway. And then the third thing is that this is the condition on the function. If I take f inverse of the boundary of y, I guess I should say x and y are, no, I'm not requiring y to be compact, but I don't want, you can make reasonable definitions of Morse functions on non-compact manifolds. We certainly want to consider the case of mapping to R, but we always want to think of our domain as compact for this setting. And then if I take f inverse of the boundary of y, whatever that is, that should be equal to the boundary of x. The first time you look at this, you might think what you want to say is f of the boundary of x equals the boundary of y, but the problem with that is that that doesn't preclude the possibility that something in the interior of x goes to the boundary of y as well. So this is really the right way to say it. Okay, so I claim that this really, one way you could say, you could this doesn't mention cobordisms, but the point is, if y actually is, if y has non-empty boundary, then it must be an interval, if it's connected. And if it's an interval, then you can just immediately say that the boundary of x splits into two parts. Those things that go to 0 and those things that go to 1. And then that becomes the cobordism structure. But very often what you want to think is that x is actually given to you with the cobordism structure, in other words, with the splitting into two, of its boundary into two parts, and then you want to require that the 0th part go to 0, the 1 part go to 1. Okay, so now some theorems about Morse functions that we don't prove now, we'll prove much later, but we state them so we can start doing topology. The first theorem is existence. And I know from seeing into the past that the proof of this theorem was never given very precisely, but it's good enough, and it's a very standard result, and the proofs exist out there in many different resources. So the proof goes like this. So given any compact n-dimensional manifold X, there exists a Morse function on X. And that's all that's exists a Morse function. Okay, so what's a slightly more precise way to say that? Actually, maybe I should even more precisely, I could say, given any x and any compact x and any compact y and any function from any function whatsoever, any smooth function from the boundary of x, I didn't put x there, any smooth function f from the boundary of x to the boundary of y. Now, of course, y is one-dimensional, so the boundary of y is zero-dimensional. So a smooth function from boundary of x to boundary of y just says this component goes to the 0, this component, which components go to which thing, right? Which components of boundary of x go to which components of boundary of y, that's all that data is, but saying it this way kind of sounds nicer. Given such a thing, there exists an extension of f to a Morse function f from x to y. So you're allowed to specify what happens on the boundary. And then the other things that we'll talk about later is that also these things are generic. This is just says there's one only. I mean it guarantees the existence of one. But really Morse functions are generic, which means that another way I could have said it is given any, maybe this would have been the best thing, given any smooth function from x to y, there is an arbitrarily small perturbation of it so that that's a Morse function and without changing what happens on the boundary. And the other part of generic is that if you have something that is Morse and you perturb it a little bit, it'll still be Morse. But that'll be discussed more later. But the point is there are lots of them. Okay. So we have Morse. If we ever want to use a Morse function, we can say there is one. Now let's talk a little bit about the critical points. This is a funny definition because it says for every critical point P, well what it really should say is for every critical point P, there exist coordinates and there exists an integer K, such that blah blah blah. And one of the immediate things you should worry about then is there any reason to think that in a different coordinate system you would have the same K? There might be many different coordinate systems putting F into this form, and the answer we will see that there is only one. There's a unique K, which is called the index. So that's state a theorem, which we'll also work out later. But this theorem is kind of sort of central to proving the existence of Morse functions as well. And this is some local theorem. It says that, now you think I'm not talking about x anymore, but of course everything, this is a purely local result, so I can just talk about what's happening in Rn. So if I have a point in Rn, right, and if this point is a critical point of some function f from Rn to R, okay, so P is a critical point, and suppose that such that the Hessian HF at P, subscript of P. What is HF sub P? At P, that's the matrix, the n by n matrix of all second partial derivatives of F. Okay? If this is non-degenerate as a symmetric bilinear form. So remember, this is symmetric because mixed partial derivatives, mixed partial derivatives, it doesn't matter how you take, in which order you differentiate. So if this is non-degenerate as a bilinear form, so it's symmetric, so therefore you think of it as a bilinear form at the point P, then F is locally Morse. So I think in the first lecture I might have given this notion of locally Morse, but what that just means is that, i.e., forget all the boundary stuff, i.e., there exist coordinates in domain and range with respect to which this F near P is equal to this sum of squares, right? I'm just going to write, well, no, right, I want to say something like K, so I'm going to write down. Okay. So P is the only critical point in here is 0, 0, 0, 0, 0, 0, 0, and that's going to be mapped to 0. So the coordinates are around P, but they turn P into 0, and they're around f of P, but they turn f of P into 0. Okay, so that, and then furthermore, so this is, I guess this is, this may be called the Morse mode. So it says you just have to check the Hessian. This sort of almost right away tells you why Morse functions are generic, because you kind of generically expect a bilinear form to be non-degenerate. What? Maybe I should back up. What does non-degenerate mean? Non-degenerate means that bilinear forms can be diagonalized. Non-degenerate means that when you diagonalize them, you have no zeros on the diagonal. And you kind of imagine, which you know, is saying that the determinant is non-zero. So it sort of seems clear that that's kind of a polynomial relation. It should be being non-zero should be a generic property there. And also, if you perturb it a little bit, it should stay non-degenerate. Okay, so furthermore, this index of P, which is this number K, what is it equal to? This is a definition of the index of that critical point. Its equals is the index. There's a different notion. I mean, the reason it's called an index is it's the index of HF of P as a bilinear form. So what is the index of a non-degenerate bilinear form? Well, you diagonalize, and then you count the number of minuses and the number of pluses on the diagonal, and the number of negatives or minuses on the diagonal after diagonalizing. And the point is that if you, the point therefore is that you can just look at f, you can compute the Hessian, you don't have to find these local coordinates, you just compute the Hessian, you diagonalize it, and you get a number. Well, I guess the point is that linear algebra tells you that the index of a bilinear form does not depend upon how you diagonalize. There are many different ways in which you might diagonalize a bilinear form, but you will always get the same index. So the issue of the index being well defined independent of coordinates is really a linear algebra issue, not a topology issue or a calculus issue. Maybe just a word or two about bilinear forms, just to remind you. I mean, you know, this bilinear form, one way to think about it is like as a map from just a bilinear form B, a map from vector space cross vector space to R, or to the field that you're over, whatever it is. But an also useful way to think of it is as a n by n matrix, right? And then you think of it really as the way it acts on vectors. You put a vector on the right, and then the transpose on the left, right? And that's how you get B of one vector and another. And so what is diagonalizing? Diagonalizing, just reminding you of sort of basics. Diagonalizing means changing coordinates, right? But you change coordinates up. You don't change the coordinates of these two copies of V independently. So diagonalizing means you replace B with, say, B and then some matrix Q and some transpose of that matrix here. And so that's so the whole theorem about diagonalizing bilinear forms says that you can find some Q and so that when you take B and put a Q transpose in front and a Q afterwards, that becomes a diagonal symmetric matrix. This requires that this is symmetric to begin with. Anything else to say about that? But the point is that's very different from the kind of diagonalization the point is you're not putting inverse in front. Another way to think about it is you do row and column operations to change the matrix, but anytime you do a column operation, you have to do a row operation as well from the left. So, okay, all right. So that's kind of the preliminary stuff that we will use for now and prove later, sort of. But let's try to now extract some topology from Morse functions. So. We now know that we now have been told that on any manifold you can find a Morse function. So what does that tell you about the topology of the manifold? And so what we're going to do is, the idea is we want to use the critical points to give us insight into the manifold, how the critical points behave with respect to each other. So let's look at the simplest case, no critical points. Well, you might then immediately say, how can something have no critical points? It's got to have a max and a min. And that's true, like if you imagine a sphere, and you might take the height function, it's got to be a minimum and a maximum. However, if we, so what you really should think of is a cobordism, and a prototypical example is, say, a cylinder. And you take a cylinder, which is a cobordism from the circle to circle, and you map it to the interval, 0, 1, and such a map has no critical points. We don't call the bottom and the top critical points. They are mins and maxes that are still perfectly happy. The derivative does not vanish there. Okay, so what we want to do is suppose X is a cobordism from M0 to M1. I guess I didn't give that terminology. I didn't say that when I was talking about cobordisms. I said a cobordism is just a manifold whose boundary is split into two parts, M0 and M1. And I didn't say that then the terminology, you usually think of that as something that goes from M0 to M1. And for those who want to know more, this actually makes it into you have a category of cobordisms where the cobordisms are the morphisms and these M0s and M1s are the objects. All right, so what do I want to say now? So suppose that's true, and suppose I have a Morse function on it mapping to the interval. Okay, suppose I got this, and suppose f from x to 0 to 1 is a Morse function, is Morse. Okay, so that means f of m0 is 0, f of m1 is 1. So then the question is, what can we say about x? And what we're finally going to suppose f has no critical points. Here's an example of something with no critical points, and the claim that we're going to try to prove, the theorem is that it basically looks just like that. The theorem then is that x is diffeomorphic to 0, 1 cross M0, and under this diffeomorphism, it's a special diffeomorphism. Let's say this diffeomorphism, call it phi, and this diffeomorphism then takes, how do I want to say it? I should draw a little diagram so I can get this straight in my head. This is phi, and then I have my function f going to 0, 1, which is my given function, and then here I have, I don't know what we call it, just p for projection onto the first factor, right? And the claim is that this commutes, i.e., in other words, the original, this diffeomorphism is such that it transforms the function f into just projection onto the first factor. So p composed of phi equals that. Which means up to a diffeomorphism looks just like this, where this is the interval 0 to 1, and then this is some manifold of 0. And in particular, that also implies, another consequence of this, by the way, is that M1 is diffeomorphic M0. right? Because M1 is the top of the cobordism, but the top of this cobordism is 1 cross M0, which is differential M1. And you know, that's a useful way you might want to show two things are diffeomorphic, is to, and this is sort of used in the higher dimensional proofs, so the proofs of the higher dimensional smooth, the higher dimensional Poincare conjectures, but we'll probably not get there. Okay, so what's the idea for this proof? What I'll do is, so in lecture 3, the proof of this more or less starts from the beginning, but I'll sort of outline and sketch the how the proof of this is going to work. We're going to take our, what you want to imagine is that here's your random weird manifold, which I'm already drawing as if we already knew it's a product. So this is X, and here's M0, and here's M1, and we want to think of the Morse function as somehow a height function. And the key step here is to construct a vector field on X. And that vector field is going to, so we want to construct a vector field V on X. And the vector field should have the following property, such that if I take, one way to say this is if I take little df of v, and then so every point I have a vector v, and then little df is a map, say, from the tangent space of x at p to the tangent space of to 0, 1 at f of p, right? And that tangent space 0, 1 is contained in R. Tangent spaces to vector spaces are canonically isomorphic to the vector spaces themselves. So under that canonical isomorphism, I can identify df of v with a real number, and this should be 1 for all, everywhere. Identity equal to 1. So why would that help? Well, then I want to argue that this condition guarantees then that if you, so we will produce the diffeomorphism to 0, 1 cross M0, actually we'll produce the diffeomorphism the other way. The other direction will produce the diffeomorphism this way. And that diffeomorphism will, perhaps that should have been, probably this direction should be called phi and that should be called psi. This direction is a flow, phi for flow, I guess. Anyway, I'll keep the notation as I have. So, if I want to construct this diffeomorphism, I need to tell you where does t comma a point q go to. So I'm going to construct, well, let's just say that we'll construct phi inverse from 0, 1 cross M0 by flowing along V. And of course, it should be remembered anytime you say you construct something by flowing, what are you really using? You're really using existence and uniqueness of solutions to ordinary differential equations, which is fundamental for everything in smooth topology. Just would fall apart without that theorem. So what do I mean then by flowing along V? So phi inverse of t comma some point q. T is in 0, 1. Q is in 0. What is that going to be? That's going to be, I'll just say in words, it's the point you get to by starting at Q0 and flowing along V for t seconds, right? For time t. So in other words, of course, let's just check. Phi inverse of 0 comma q should just be q, which is good. And then the fact that this df of v equals 1 means that, so what do you want to think now? Well, how does this help us? This tells us that if you start here at q and you flow forward, you can also all the time look at f of wherever you are in this path. And f of it is going to be flowing forward along df of v. So this point, while this point is moving up here, this point is which is its image, is simultaneously flowing forward along df of v, but that's just unit length. So in one unit of time, 1 second, this point gets from here to the top, so therefore in 1 unit of time, this point q has to get from here to the top. And that's the essential idea. That's why when you get to q equals 1 cross m0, you're somewhere at m1. And so what else? What is uniqueness of solutions? We were basically using existence of solutions to get this flow. Uniqueness of solutions tells us that, you don't, well, let's see, it tells us that you can't tells us, for example, you don't have 2 points flowing to the same point. That never happens, because if you did, you could flow backwards, and then where would that go, this way or that way? You have to decide. So, in other words, and also existence of uniqueness actually implicitly in there is built in the idea that where you get to smoothly depends upon, I guess it's a separate theorem, that another theorem is that the solution to an ordinary differential equation depends smoothly on the initial conditions. And so that'll give the smoothness of this map. The fact that this map is invertible with smooth inverse also really depends upon the uniqueness of the solutions. Okay, so that's the idea, and then finally I'll just end, so do that a little more carefully next time, and then I'll just end with how you get such a V. And one thing you can think is, one picture you can have is, suppose this was actually embedded in Rn, or even R3, just imagine that, and suppose this is actually the height function, right? Then you can just take the standard ordinary Euclidean gradient vector field. Yes, upwards pointing. And then you have to just rescale it and normalize it to get 1. Now when you rescale, when you try to normalize a vector, you better hope the vector never goes to 0, right? Because then you can't divide it by its length. But you can divide it by its length to get it to be length 1, or to get it to have df of it equal to 1, as long as it's not 0. But of course it'll never be 0 because v has no critical points. So that's important. It's really the existence of this vector field v that's where you have to ask, when you're looking at the theorem, where did you use the hypotheses? And the hypothesis was that there were no critical points, and we use that hypothesis to say that such a vector field exists. But the argument that argument based on things sitting inside Rn can be generalized to arbitrary ones by taking a Riemannian metric, which is just an inner product on each tangent space varying smoothly with the tangent space, and then there's an equivalent notion of a gradient vector field in that setting. But instead what I want to do is just construct the vector field v directly using partitions of unity. And so what you're going to do is you're going to cover X with patches, and on each little patch is small enough that by using local coordinates you can argue that such a v exists. And then you're going to add them together using partitions of unity, and when you add two things together using partitions of unity and they satisfy some property, you want to make sure that after patching them together you still have this property. This is the property we want. Will that still hold after patching with partitions of unity? And the answer is yes, because this property, if we have, basically you only have to check that if you have, if v1 up to vn satisfy the property that df of v1 equals vi equals 1, and then you take some linear combination, lambda 1 v1 plus lambda n vn, you call that v. Locally, that's all you're ever doing when you're doing a partition of unity. But remember, what does it mean for it to be a partition of unity? It means that at every point, these numbers add up to 1. then that together implies immediately that df of v is also equal to v. So so I think that that's the end of everything I said some 8 or 9 months ago on that day, and I believe that if you go to YouTube and look at lecture 3, you will see this theorem started again from the beginning as it's more properly, but this is the setup for that theorem. So, I'm done.